So good evening, everybody. My name is Harry Helling. I'm the Executive Director here at the Birch Aquarium at Scripps. I'd like to welcome you this evening for the Jeffrey Graham Perspectives on Ocean Science Lecture Series. We are honored tonight to have Dr. Marty Ralph, who is the Director of the Western Weather and Water Extremes, the Center for Western Weather and Water Extremes, where he uses his experience as a research meteorologist to understand the physical processes that create extremes in precipitation ranging from flood to drought. Dr. Ralph has a long history of leadership positions in NOAA, from the chief of the water cycle branch to managing NOAA's Science, Technology, and Infusion Program, where he chaired NOAA's U.S. Weather Research Program, and led the creation of NOAA's Unmanned Aircraft Systems Program. A major goal through his career has been to better understand, monitor, and predict key elements of global water cycle, including water vapor transport, precipitation, and runoff. Marty's been a pioneer in advancing scientific understanding of atmospheric rivers, and that's the topic for this evening's talk. So I'd like you all to help me welcome Dr. Marty Ralph.
Good evening. So I'm going to give you a tour today of a topic that's been emerging the last few years. It's called atmospheric rivers, and it's got a bit of a history over about a decade now. I'll walk you through some of that, and then I'll also share with you some stuff from this winter at the end that'll be sort of timely given the kind of storms we've had lately. First of all, I'm trying to embrace the role of being at a university now. I was at NOAA for 21 years, and university professors ask their audiences to answer questions. So I'm going to start off with a question for you. Anybody know where that picture might be from? Got an answer over here? Sonoma County. Beautiful area. We've done a lot of our work up there. And I really find that one of the reasons the atmospheric river subject is so interesting is it's so vital to the ecosystems that we depend on, as well as our snowpack and our water supply for urban use and the like. And this watershed up here in Sonoma County is where we've done a lot of work. So I'll walk you through that in just a moment. All right, many of you know, of course, we had a very wet winter. This photo's from up near Sacramento, and it really illustrates the kind of heavy winter we've had up north. And I think most people have heard a little bit about the Oroville Dam spillway issue, and I'll touch on that towards the end of the talk as well. But this shot really shows how the Central Valley can fill up with water in a way, at least parts of it there. And that channel in the middle is called the Yolo Bypass, and is an area that is allowed to flood and relieve pressure on the main river that otherwise goes through Sacramento. There's an amazing infrastructure in California focused on managing these extremes in weather that we experience in terms of precipitation from flood to drought. And I'll step you through that again in just a moment. All right, first the outline. What is an atmospheric river? I'll give you a hint about that and some background on it. Then the question, can we predict them? And the short answer is yes, but I'll give you some nuance on that. And then, can atmospheric river information potentially be used to help operate reservoirs differently in the 21st century than we've done before, in a way that might help reduce flood risk and also mitigate drought? And then at the end, I'll add a little special sauce with this last winter's activities. All right, so where did this topic come from? In meteorology, a lot of emphasis. I'm an atmospheric scientist. I studied meteorology, got my PhD at UCLA. Sorry, UCSD, but I'm back at UC, so I really like that. And I have a guest from the University of Arizona here, well-known professor, Zubin Zhang, and I got my bachelor's degree there many years ago. But this picture shows an illustration of the dilemma. Take a look at this satellite image, which is sort of a classic one. There's the West Coast, and here we see the low-pressure center and all these clouds with a funny color scale for the cloud structures. But notice the low is really sort of, you're drawn into that spot. And our field is focused on that part of these storms for nearly a century. And the problem is that there's a lot of action outside that spot. And here we see, for example, in southern, way south of there, is where the heaviest rain was. A foot of rain, several feet of snow. This was from a few years ago, but it's very representative of what happened this winter. And then we had large waves down that way. And then I want to highlight that this 500-mile displacement, between the low center and where the action is from the water perspective is quite substantial. And it's not always the same distance. The punchline is, in meteorology, we've done a lot of work to get this right, but getting this right, the low pressure center, doesn't by definition mean you get this right. So we're doing a lot of work to try to unravel what goes on in determining whether that part of the storm is going to be strong or where it'll hit and how long it'll last and that sort of thing. All right, and here's a nice illustration of how complex it is. This is a set of, this is a loop of satellite images, and the color fill is what's called integrated water vapor, or IWV, I'll call it. Imagine taking this room and going up to space, grabbing every water vapor molecule on the way and bringing it back down to the ground and condensing it into liquid. It would only be about that deep, and that's where all of our rain comes from, is that little bit of water vapor in the atmosphere. And if you look at this view right here, what you're seeing is how that integrated water vapor is distributed around over the Pacific, part of the Pacific during this period. This is a dry region here. The reds are very wet. That's the tropics. And then you see this yellow and orange and green hitting Seattle, then fading in California. Then look at this firing up. And now we have that one hit. Then the next one came right on its heels, stalled, a gap. Then the next one came in big and hit hard. Those are atmospheric rivers hitting Northern California. Those three storms over the course of about a week produced 25 inches of rain in some locations, which was about 40% of the precipitation for that year. Notice this date here, December 2012. I guess this was about 2 weeks. That was actually the last real wet period we had until the drought began. And the problem is that we have to deal as a state and the West in many ways with these big events that can produce an amazing amount of precipitation and potential flooding. But then if we don't get them, we don't get enough of them, we end up sliding down into drought. And that's what's happened, and I'll tell you more about that. All right, well, how do we measure these things? From a research standpoint, one of the great tools we have, thanks to NOAA and the National Oceanic and Atmospheric Administration, the National Science Foundation, NASA, Department of Energy, these federal agencies actually maintain research aircraft and other facilities, including Scripps, fantastic ship facilities, to go out and explore the world and explore our natural world. And we've taken advantage of those facilities from various agencies, all of those I just mentioned, to study atmospheric rivers. And one of our key approaches is to take one of these aircraft. This is normally dedicated to tracking hurricanes in the Atlantic or Gulf of Mexico, and we borrowed it to come out here and in the Pacific, this is the West Coast right here, to study atmospheric rivers. And at the point in time this is from, I'd done over the course of several experiments, 17 different flights with this aircraft where we crossed atmospheric rivers. The color background here is the frequency of atmospheric rivers. That's Hawaii, there's California. You see they're more frequent out here. Yellow means they're more frequent than blue and that sort of thing. Each one of these white stripes represents the track of this aircraft or a related aircraft as we crossed an atmospheric river. And when we did that, we dropped something called a drop sonde out of the aircraft. It's about the size of a Coke can, made out of cardboard, and it has a thermometer, and it measures the pressure and the moisture and the wind as it descends. Has a little parachute, takes about 20 minutes, 30 minutes to float down, and it radios back that data to the aircraft. And as it does so, we record it, and then afterwards we can go in and analyze what the structure of the atmospheric river looked like. And I'll show you what we did, what we found if we average all 17 of those. Here's what it looked like. I won't show that map, that's a little too detailed. This is a vertical cross-section over about 1,000 kilometers, and this is vertical up to about 10 kilometers in altitude. And the color is the water vapor transport, the horizontal transport of water vapor. So you remember that loop I showed that had the integrated water vapor? You notice how it was moving? Well, that's the water vapor moving, and that's the key thing. That's what makes it more like a river. It's movement of water vapor in the atmosphere. It's just moving as water vapor instead of like a terrestrial river, which is liquid. So this shows us how that is concentrated. In fact, 75% of the integrated vapor transport, that's IVT, occurs in the lowest several thousand feet. So unlike the jet stream, which most people have heard of, and when you fly commercially like East Coast to West Coast, you might hit 100, 150 mile an hour winds up there. Problem is that air is bone dry normally. It can hardly hold any water vapor. It's so cold. When you get down low in the atmosphere, though, the warmer the air is, the more water vapor it can hold. So the atmospheric rivers are really concentrated in the lowest several thousand feet of the atmosphere, not up at the jet stream. And that's one of the things that makes it harder to measure. But how much water vapor an atmospheric river transports is one of the reasons we took these aircraft out. And it turns out that if you look at an atmospheric river sort of from bank to bank and ask how much water vapor is flowing, and compare it to how much liquid water is going down the Mississippi River, it's about 20 Mississippis worth of water. It's just in the form of vapor instead of liquid. And in fact, our most recent analysis, we've added 4 more cases to this from last winter. We're now up to about 25 Mississippis as the average of our 21 cases. That also corresponds to about 2 Amazons. So we're coming up with new units here. And if anybody's into water at all, you might know what an acre foot means. And you can pretty much guess what it is, right? It's an acre of land area with a foot of water on it. That's enough water, by the way, for about 3 or 4 households for a year on average. All your gardening and water in the house and all that. And 1 atmospheric river, if it transports for a day, you add up the amount of water that goes by in a day in the form of vapor, it's about 20 million acre feet. So if you think of the Sacramento River, I know most people don't have numbers in their heads around this, but the Sacramento River, the biggest river in California up north, its whole discharge for the year is about 25 million acre feet on average. So this is essentially the equivalent in one day of the amount of water that is coming down the river, the Sacramento River, in a whole year. Now what's the difference? The difference is not all of this rains out, right? We have to have clouds and precipitation to make that water, turn that water vapor into water on the ground. And that's a huge area of research also at UC San Diego and at Scripps Oceanography. We had a program called the CalWater program where we brought aerosol scientists like Professor Kim Prather from the chemistry department and myself on atmospheric rivers and Dan Cahan from Climate World. And we studied these atmospheric rivers and their interaction with aerosols. It's really a fascinating topic and one of the cutting edges of research. All right, another thing that's happened is that the term and the concept has gotten a little bit, there's been some interest in it in the media. And one of those, one thing that resulted from that was an invitation to do an article in Scientific American. And Mike Dettinger from here and USGS and Laura Ingram from USGS teamed up to write a summary article on atmospheric rivers that was published in Scientific American a couple years ago. And you see the nice schematic of the stream of air moving across the mountains, rising, causing precipitation, and so on and so forth. And you can see it's fairly narrow. The real atmospheric river events tend to be about twice as wide as shown here schematically, but you get the idea. They're sort of narrow ribbons of water vapor transport. It turns out that if you look around the planet, let's say we went from here, if you can visualize with me for a moment, and go west all the way to the horizon and keep going all the way around the planet. And you imagine that distance, right, the circumference of the Earth at our latitude. Now imagine as you're going along, with the work we've done, you could immediately identify when you were in an atmospheric river. We know those conditions. You'd cross one somewhere near Hawaii probably, then you'd cross one maybe near Japan, then another one at the Atlantic, and maybe there's another one over the East Coast or something. There'd be 4 of them. And if you added up the distance that it took to cross each of those, it would be less than 10% of the circumference of the Earth. So it's really narrow. But if you look at all the water vapor transport that's happening, it's 90 to 95% of all the water vapor transport in the mid-latitudes is happening in these narrow ribbons. So they are really vital for our precipitation, they're vital for our climate, they're vital to determining the future of our water supplies out here as we wonder about what may happen in the future. Where do they occur and make impacts in the western U.S.? This yellow area highlights where we've shown in scientific analyses that ARs are really important to extreme precipitation. Sidebar, I'll call atmospheric rivers ARs for short. And this spot in star is where that photo was from at the beginning, Sonoma County, which has the Russian River flowing through it, and there's a reservoir there I'll talk about in a few moments. Another thing we've discovered, and this is very nice work by John Rutz, who got his PhD on the subject a couple years ago, is how does this water vapor get into those areas? If you recall that last slide, well, you know, they hit the coast here, we know that, they hit the Sierras, but how in the world do they get into these areas? Well, it turns out they have a very interesting approach. They actually go around the mountains a bit. So where the air can make it through low points in the mountains, that water vapor can get through without raining out as much and ends up being a pathway into the Intermountain West, where we believe that these produce a significant fraction of the heavy rainfall there as well. And now we can ask the question, now that we know how to track these and count them and see where they're at and when they're there, we can look at how much precipitation falls when they occur. And here's a map that shows the fraction of annual precipitation on average that occurs because of atmospheric river events around the western U.S. These numbers here are hard to read, sorry. The blues are around 10 to 15%, light blues around 25%, yellows and greens around 35, then up to 50% and 60% in the reds. So what we see is basically the coastal areas get somewhere between 40 and 50% of their annual precipitation from atmospheric river storms, even into Arizona in the range of 40%. Then you get up in here and it's much less. There are a lot of other types of storms that contribute. And if you think of an AR coming from the west here, notice this sort of low point here. That's like an area that's blocked from AR precipitation because the Sierra Nevada are right there. And it sort of soaks up the water vapor or the water out of the ARs before it can get there. So we don't get as much AR precipitation there. All right, we can also take a look at individual storms as they hit and figure out whether they're an atmospheric river or not. And what we did, the group here at Scripps I work with, we had a little contest in a way. We had the group look at all the storms in this water year. I think this was 2016, last water year, a year ago. And we asked the question, if we look at the precipitation all year long, and this is a graph from October to October. The water year, by the way, runs from October 1st each year to September 30th the next year. And this on the vertical is the cumulative precipitation in this region in Northern California, where a lot of our water comes from, even down here. And this is called the 8-station index. And the light blue color is the average, which conveniently turns out to be 50 inches a year. And that data goes back a century. And this dark blue curve shows the actual average of that data, those 8 stations, last year, a year ago. And notice how we were above normal finally after several years of drought. We ended up beating normal. But we asked the question, look back at each one of these big steps. See how those occur like that? Each one of those we identified objectively as which ones were the top 10 wettest storms. And then we went and looked at our objective criteria to ask the question, was each of those storms an AR event or not? It turned out each one of them was. And as you can see here, the total 54% of the water year precipitation in this key watershed was during these atmospheric river events. And by the way, much like that loop I showed you, about 25% of the whole water year precipitation fell in about a week in early March. We call that sometimes in California a miracle March, because it was pretty darn dry up until then. All right, another thing we have unique in this area is how variable our precipitation is from year to year. How many people here are from east of the Mississippi? Thanks for admitting that in this area. I'm from Michigan. I lived in Florida, Colorado, Arizona, California, et cetera. What happens in much of the country is you may have a single season that's unusually dry, but you have a chance to get wet every season, so you sort of have odds of making up for it. And what this shows, the pink dots here represent how from one year to the next, the variation in annual precipitation back east is very small, just plus or minus 10% or so. Then you get into the Intermountain West, and it's plus or minus maybe 25%. Then you get out here, and look how green California is. That's supposed to be a joke, sorry. But we're actually a little bit blue in the south. Ooh, there's another one. Sorry. No, I'm not going there. I'm not going there. In fact, the normal Mother Nature gave us in California is that we have about 50% variation from year to year on average. So if average is 40 inches, let's say, in a year in a wet place in the Sierras or something, it's very common to have only 20 inches and equally common to have 60 inches. And what that does is it creates a need for a lot of special information, special tools, special advice for water managers. And as a meteorologist trained in many of the traditional topics in our field, the solutions that work back here in meteorology don't necessarily solve the problems out here. This is one of the reasons we've created a new center. I've created a new center here at Scripps, the one you heard about, Center for Western Weather and Water Extremes, because we have some really special needs. And this map, as much as any, really highlights an example of that. All right, and why is this so variable? Is because we really have one shot at our water year. We get a little bit in the monsoon in the very southeast part of the state, but mostly we have 5 to 7 months each year during the cool season where we either make or break our whole water year. Most other parts of the country have multiple seasons where precipitation can be significant. All right, can ARs be predicted? Short answer is yes, and let me give you an example, to a degree. Let me give you an example here. This is now, it's a little hard to see, sorry, the gray here is the continent. There's Baja, California, British Columbia, Hawaii's out here. And the color fill here is that integrated water vapor. You remember that term? This is what it looked like as a forecast 2 days before a storm hit. This would have been about a year ago last week. And this is that integrated vapor transport. See that red? That means it's very strong. Our scale here, this strength atmospheric river happens maybe once a year on average. And you can see how this was predicted to be here, and this is the same time, and you see the water vapor transport into the state. This was 2 days ahead of time. I'm just trying to illustrate the fact that our weather prediction models can produce atmospheric rivers in them. Do they get them right every time? No, but we're starting to measure how that works. So if you think about this last slide here, you could imagine pinpointing where that hit the coast, here in Northern California. Imagine now looking at the forecast from a day before and asking, did it predict the AR to hit that spot? Or ask it from 5 days earlier, is the AR going to hit that spot? And then we can calculate the error in the position of the AR landfall, as we call it. And then we map that over multiple winters with the best weather models on the planet. And we see if you look out 10 days ahead and you measure the error in landfall position in kilometers, what we see is these different models from all over the world show the same sort of thing. That at about 5 days lead time, we have an error of about 500 kilometers in the landfall position. That's like saying 5 days from now, we think an AR is going to hit San Francisco, but instead it hits LA. Or it's going to hit Seattle, and instead it hits south of Portland. Those are big errors for people on the ground, people who worry about water management or flood. They're huge errors. They're much bigger than the watersheds themselves. Improving on this curve is one of our reasons for the center. We think that with a dedicated effort over years, we'll have a chance to really beat down that error to a lower value. In my old job in NOAA as a program manager, I helped support funding for research on hurricane forecast improvement, and there was a classic parameter, the hurricane landfall forecast error. And that, through a decade or more of research, we've cut that in half because of the advances science can make, and the National Weather Service took that on and have now been producing much better forecasts of hurricanes in the last several years than we ever had before. Part of the goal here is to bring that level of effort and attention to our western problems, the equivalent of which is essentially the atmospheric river topic. I want to highlight that one of the reasons we have a chance to do good work here is that the UC San Diego has, as part of its family, the San Diego Supercomputer Center, one of the state-of-the-art computing centers in the nation, funded heavily by the National Science Foundation. In fact, just recently they won a major grant that only 2 other supercomputer centers nationally were awarded. They have massive computing capability, and we're partnered with them very closely. And you can see the director there in the middle on the right is Mike Norman, and he's an astrophysicist and has very deep interest also in our work on atmospheric rivers. So he's been a big supporter. And I'll also mention that one of the reasons we think this is so important is we're developing a weather model. There are different types of weather forecast models. There are ones that have been developed specially for hurricanes, especially for tornadoes, especially for air quality, or for fire weather. You can imagine. No one's done one for atmospheric rivers, so that's one of the things we're taking on here. We're inventing a weather model tailored to the atmospheric river problem, and we're using observations that Scripps and our partners and our federal agencies can help us collect to evaluate the model to make sure we're getting it right. And that's a really big trick because it's tough to get the models right all the time. And to have it focused on the West rather than also trying to predict weather elsewhere also helps us plan for success. One of the other things we've done is recognize that when we want to predict an atmospheric river landfall, get the location right, for example, it's very important if that atmospheric river is offshore that we know where it is exactly offshore and the details of it, the winds in it, the water vapor in it, the precise information about it. This is a satellite image of an atmospheric river last winter. There's Hawaii and the West Coast. And these lines represent the tracks of 2 C-130 aircraft that we were able to deploy last winter to sample this AR with a lot of dropsondes that got back into the National Weather Service forecast model. And we're now in the process of doing the very time-consuming work of rerunning the model and figuring out, did those data improve the forecast of this AR making landfall? And frankly, what we're trying to do is envision, and we have partners thinking about this deeply, a reconnaissance program using aircraft to better predict atmospheric rivers on the U.S. West Coast. Our nation has done that for hurricanes for as long as I've been around, and it's about time, I think, that we have that kind of investment in our Western problems. As you can imagine, the details of where these hit especially given what's happened this winter, are very important. All right. Next, I want to highlight one of the applications we're working on, and this is with a lot of colleagues in the water management community, civil engineering, Army Corps of Engineers is one of our key partners, Sonoma County Water Agency as well. And I'm going to highlight this region I've been talking about up in the Sonoma County. There's San Francisco, Monterey Bay, and here's the Russian River. That's where the William Sellum Winery is. That's where the other winery is. You know, get the idea. We have a brutal job studying the weather up there. But we have great partners. It's a fantastic area to do work. It is ground zero for atmospheric rivers. It is where more atmospheric rivers contribute more to annual precipitation in that area than anywhere else on the West Coast. It's the perfect place to go meteorologically. Here's a little bit of a complicated diagram, but I want to really dig in for a moment on this. This is 2.5 years on the horizontal axis from left to right. On the vertical axis on this side is the amount of water behind a reservoir called Lake Mendocino, and it's expressed in acre feet. So 100,000 acre feet, for example, is right there. On this side, we have cumulative rainfall in inches, and the green curve is the rainfall accumulated over those 2.5 years. And notice, for example, these big bumps up. Well, we now know those are ARs. You know, we would look at the other information to confirm that. We've looked at this case very carefully, and there's a big one, and there's a big one. And there, trickle came in, and then it stopped basically for a good portion of a year. The blue curve on it is the water level behind the dam. Notice how it goes up and down, and it spiked right there, and then it descended down. This is the descent into drought that we experienced in late 2012. This is that atmospheric river that I showed you the loop of earlier that dumped 25 inches of rain in a matter of 2 weeks. Actually, it was a pair of atmospheric rivers in this case. Notice the year before, this is March. We had a miracle March on that watershed in early 2012. The gold curve, the punchline here is that's what's called the rule curve, and that's the guidance that is officially has to be followed when a reservoir operator is deciding whether to keep water or let it go. And it is low here at this time of year because it's needed for flood control. And then in the spring, after the storms subside and there's no flood risk, it can refill and be used for water supply through the summer. And then if there's extra water, it needs to be drained down. And then in the winter, if there's a storm comes in like this, it needs to be drained back down quickly to restore that flood control capacity. We saw the need for that very heavily this winter. However, in this case, the drought began. And it turned out that extra water would have been very useful if it had been retained in some way. And that fact is what led to the creation of this new program called Forecast Informed Reservoir Operations. And we're working with Sonoma County Water Agency, which runs the water supply operations, and the Army Corps of Engineers, which runs the flood control, and NOAA, which deals with and regulates fish. So this river also has 3 species of salmon, one of which is endangered, the coho. It was really at the brink of extinction about a decade ago, and now through restoration efforts, it's recovered substantially. It's still endangered, but it's better, and the other 2 are threatened. So the Water Agency, the Army Corps of Engineers have to operate this system in a way that also helps the fish recover healthy populations. That means keeping water in the stream when otherwise there might be not enough water. And Sonoma County Water Agency, by the way, provides water to 600,000 people and an incredibly productive and vibrant agricultural sector, as you can imagine. So our committee, we formed a steering committee to work on this idea, and we're doing it as a hypothetical. What if we could have good enough forecasts that some reservoir operator could potentially keep some of that extra water in the middle of that, at the end of that storm? If that water's now behind the dam, and they look out in the forecast a week ahead, let's say, and there's no atmospheric river coming, sidebar, realize that floods don't happen on the Russian River unless it's an atmospheric river event, essentially. So it really boils down the weather prediction to, is it going to be an AR or not? So if the reservoir operator can look out ahead and has reliable information, maybe they could hedge their bets and keep some of that extra water, knowing that they'd have enough lead time to release it, enough to get it out of the reservoir, which we think could take about 2 days, and then 3 days to get past harm's way. So we're thinking about a week's lead time. And I want to highlight, it's a very interdisciplinary problem. We have engineers, we have climate scientists, we have hydrologists, meteorologists, water managers, biologists, and economic folks. all working together. We developed what we call a work plan for 5 years of effort to explore this and test the viability of whether or not this idea might work. If it does, we could potentially take advantage of this existing reservoir to keep more water, or to even add flood control, because if a storm's coming, we could potentially release more water before the storm, knowing it'll refill. And that's a trade-off between the water agency, whose job is to deliver water to its customers, and the Army Corps of Engineers, whose job is to protect people from flooding. That trade-off means that we potentially could take advantage of this same facility, gain water supply reliability and flood control without moving a drop of concrete. That has the potential to really revolutionize water management in the West, and that's what this committee is all about. And we're taking it very seriously, looking at how this might work. This is an example in a time series mode schematically where there's that 10,000 acre feet of extra water. Remember, that's like enough for 30,000 people. And imagine we had been able to do that when 2012 came along. That water would likely have been available then later in the year to help us deal with the drought situation. All right, let me turn now to this last winter and highlight a couple of events that occurred and illustrate where we're at on understanding them and predicting them. Here's an example from early January. This was a very strong atmospheric river. We see that this is now the same sort of water vapor image. It's got a different color scale, but you see that long, narrow feature hitting the coast. There's our Lake Mendocino. That hit. It turned out this AR was as strong as we would normally see only about once every 3 years. And we've just developed the methods to quantify that. Here's what we're looking at now. Remember that 8-station index in the Northern Sierra? That's what this shows. Sorry this is so fuzzy, but this is the year. This is the inches of precipitation accumulation. That's normal. The green curve is the wettest year on record, and the blue curve is this year. We're way ahead of the normal, way ahead of the record, and it's really the wettest year to date that we've seen in California's data in a century. And as of a few days ago, we were at over 200% of normal for precipitation. Now, the storms have shut off for the last week or so for the most part, so we're sort of tracking horizontal on that chart now. Now, how much of this winter's precipitation was a result of atmospheric rivers? We now have the methods to look at each storm and ask the question objectively whether or not it was an atmospheric river event. And we can identify objectively, if it was, where did it hit the coast first, or actually strongest, and then we mark it with an arrow. And this diagram shows all these different arrows coming in. Each one represents a different atmospheric river hitting the West Coast somewhere. Now, an arrow might hit right here, let's say. Doesn't mean that AR didn't hit farther south. Often these will propagate south, but it was strongest at this point, so that's where we show the arrow. There were over 30 atmospheric rivers hit the West Coast, 30 in California alone. Normally, we might see about a dozen. So we're well over double normal. Remember that precipitation is well over double normal. So you see them sort of complementing one another. The other thing I want to highlight is we now have a scale for the strength of ARs, weak, moderate, strong, and extreme, based on how much water vapor transport they're doing. And we've color-coded these accordingly, where red are the extreme ones. And in this case, each of these 3 red ones, on average, would only occur about once every 3 years. So we're seeing, not only are we getting more atmospheric rivers this winter hitting the West Coast, but we're also getting stronger ones than we would normally see. Hence the problems we've encountered, such as is illustrated by this amazing photo of a scary situation at Lake Oroville. This is the primary spillway, and it had developed a problem up here. It was eroded and cracked, and they stopped it for a while to look at it. The storm that was hitting added a lot more water behind the dam, and then they realized that the forecast said there'd be a certain amount of precipitation and runoff. It ended up being quite a lot more, so they had to start playing catch up, and they decided that they're basically going to have to give up this spillway, and they released a huge amount of water in the process, and it really wrecked that spillway. But they also knew, I understand from folks in the area, that there's bedrock under here, and there was really no worry, even though the cement would go away, that it would create a really catastrophic problem. It just was a lot of water coming out. And the brown here means it was eroding the dirt beside it. But nonetheless, it created a problem because the water came in faster than anticipated. This, even though they opened this wide and it really eroded this away and cut off a bunch of dirt here, The emergency spillway right here ended up coming into play, and water flowed over that and came down through this area here in a way that ended up starting to erode right up against the base of that spillway, and that's when the major evacuation took place. There was some concern that that emergency spillway might have had a breach, and it would have released a lot of water off the top here. Now realize there's bedrock under here. This is safe from the main dam, and my understanding is the experts were never really concerned about this dam, about the dam, but more about having a lot of extra water coming down there, more than normal, for some period of time, hence the evacuation. Well, what did this look like meteorologically? This is a map. It's zoomed in. There's this is the Sierra Nevada, and the background is the terrain height in color. And the color contours here, you can't really read them very well, and I'll highlight the 18 inches here. This is the 5-day observed precipitation in this region right above Lake Oroville, and it's a large area that ended up getting that. The yellow area outlines the Feather River that feeds into Lake Oroville, and you can see a photo of the emergency spillway starting to release water, and you can see the erosion going on down here, which is partly why they started to worry. And here's an example of one of the forecast evaluation things we're doing, looking out 5 days. This is lead time in hours, and this is rainfall in inches. The black is what occurred officially during this period at this, on average across this basin. And here's what the forecasts were prior to it. The forecasts were only about 60% of what was actually observed. And then about a day ahead, a couple of the forecasts got in line. These ones are the official forecasts. And this red one here is that special model I told you that we're inventing. We started catching on a little bit to how strong this was going to be. Here's an illustration of that very storm in early February. And you can see the loop here, and it hit very strong up in here. You see that very strong plume. Notice it combined two things, came in there, hit very hard, stalled for a bit. And it turned out there were 3 ARs in a row. I'm only showing one here, and they came back to back to back. And the second one was the real kicker. It really put things over the edge for that watershed. All right, this is a very nerdy diagram. I won't go into too much detail except to say that this big arc you see right here tells us that the forecast, part of the reason the forecast didn't catch this right a few days ahead is that it was predicting the atmospheric river was going to hit up here instead of down here. This arc tells us basically where the forecasts were saying at 10 days lead time or 8 days lead time it was going to hit Oregon. Then at 5 days lead time it was going to hit, north of there. At a couple days lead time it was going to hit right where it did, or close to it. So we see these forecasts of the AR landfall varying over time. I'll skip that. I already mentioned that we're above the previous record for water year. Where are we headed, or where are we at in another diagram? This is a beautiful analysis by Mike Dettinger of USGS, also part of our center here, going through the water year. And this is millions of acre feet of storage. In the dark blue is in reservoirs, and in the gray is in snow. And that's the averages. The blue that's the average reservoir levels, and the gray is the average snow level. And what we see here in the yellow is the current reservoir conditions up through today, essentially. And the orange is the snowpack. You can see the snowpack is way above normal. And this was, I believe, 2011. And this was the record in 1983. So we're still pretty far behind those, but we've got about a month to get there. And depending on whether or not these ARs turn back on or not, will determine whether we get up to that level. Very quickly, San Diego, we're at 110% of our total for the year, the normal for the whole year, and we still have the potential to get a few more storms. And I won't go through that too much except to say that the odds of reaching 125% of normal in each of these different areas, basically we're already there, so we're way ahead of where we should have been. And then even reaching 150%, there's a good 3/4 odds for the center part of the state. We've even got a fighting chance of about 40% chance of reaching 150% of normal here in the southern coastal area. All right, just a couple closing slides here. This is a little summary of our center for Western Weather and Water Extremes. I suggest if you're curious about this stuff, just Google us. CW3E is our nickname. Nobody else is foolish enough to have that as their acronym. But we work on problems in the Southwest. I've talked a lot about atmospheric rivers here. We're also interested in the monsoon, and I mentioned a colleague from Tucson, Arizona is here, and we're working with them on this as well. And then there are other types of storms as well. There's our weather model. We're looking at seasonal outlooks, climate science, tools for California water extremes, and this forecast-informed reservoir operations topic. Here's our website, cw3e.ucsd.edu, and I just want to close quickly with 2 slides. One is to show some of the group, some members of our group that happened to be here about a week ago for a group meeting. You can see we have grad students. A couple of those are here. Tashiana Osborne I saw, Miriam Lamjiri as well. And also we have a couple of postdocs here. I believe Forrest Cannon is here today. And we also, Brian Henn is here but wasn't able to be in the photo. But anyhow, the point here is we're building up a team of very interdisciplinary folks from engineering, from climate, from meteorology, from atmospheric science, from oceanography, and we have faculty members working with us, including Joel Norris and Amato Evan, Sasha Gershinov, and others as well who aren't shown here. And we've got a really talented group of people starting to look at this atmospheric river problem from many different directions, from understanding them physically, to better measuring them, to better predicting them, to anticipating how that better information might be useful in decision making. And then finally, in a very remarkable circumstance, I didn't do this on purpose, Harry, but my last slide is about this remarkable Weather on Steroids event that is now underway at La Jolla Historical Society. It's a beautiful arrangement, and Sasha Gershinov, who I mentioned a moment ago, was one of the organizers of that. I hope he's on your panel. And then finally, that this image in particular is 2 of the artists chose to highlight atmospheric rivers in their art, and I recommend this sculpture to you. There's the North America, and there's the AR coming in to hit it. It's out on the front of the lawn. Oscar Romo, very talented artist, had a great talk with him. So thank you very much, and I'll take any questions if there's time. Good question. Are the aquifers better from all the rain? Have they benefited from all the rain? I'm not a groundwater expert, but I have heard from people who work on that there has been recharge occurring, but it's likely to be multiple years of wet weather required to refill some of them. Some of the aquifers are doing quite well. I was just up in Orange County a couple weeks ago, and they manage their groundwater very well, and they said they're in good shape right now. But some of the aquifers are going to take much longer to recover.
Last year we had an El Nino, and I noticed you never mentioned that once during the whole talk. And I was just wondering, is there a relation between El Ninos and ARs? Or this is the rain that we expected last year that we've gotten this. ARs are more impressive than an El Nino at this point.
Could you write that down? Yeah. That's a really good question. And in fact, because of the strong El Nino last year, there was a lot of anticipation of a potentially wet winter here. And the problem is that those predictions were based on 5 strong El Ninos observed over a century. 4 of the 5 had been very wet here. 1 of the 5 had been dry. So in a way, what we did is we drew the wrong card out of the deck. Even though the deck was stacked in our favor last year, we drew the wrong card. This year, La Nina, not supposed to be so wet down here, well, we get hammered. It turns out that the talk I gave here, I think, illustrated that we've learned now that there's this more short-term phenomena called atmospheric rivers, which really determines whether we're wet or dry. What controls whether or not we have more or fewer atmospheric rivers is a subject of research. El Nino or La Nina appears to influence some of the stronger ones, the probabilities of that, but it's not the same as predicting outright that we'll get them. There are things happening in the Arctic, there's things happening in the tropics and the Indian Ocean that appear to influence the storm track in the mid-latitudes, which is where the ARs reside. And those are the things we're working on now. Great question.
Thank you for a great talk. How do you or will you get the data daily or hourly or whatever it is for these AR models that you're doing so you can tell people what's going to happen?
The question was about how do we get the data at high resolution and the likes. Well, there's a lot of different observations that go into weather prediction. And a lot comes from satellite. We really depend critically on the satellite observations. Some of those are hourly, some of them are more frequent, some are twice a day, that sort of thing. But there are a lot of different types. Also on the ocean surface, we have measurements of the ocean surface temperature from an amazing array of buoys that Scripps actually has had leadership in. That ocean, that upper ocean section in about like 100 meters down, the heat in that is really vital to feed these ARs. So we have to get those right. So there's actually an array of thousands of these buoys out there that Scripps invented and has deployed that sit at the surface for a while and then descend automatically and then come back up and release their data. So we depend vitally on those. And then these aircraft measurements we do periodically over the ocean. But over land, we have radars, we have thermometers and rain gauges all over the place, and we use all of that. So it's a very complex system, in fact.
Do the atmospheric rivers generally follow the Gulf, the jet streams?
Do the atmospheric rivers tend to follow the jet streams? The jet stream, the short answer is yes. Not exactly, and they can be angled differently, but the upper level jet stream is part of the storm track. And the ARs occur basically within the storm track to a large degree. It's not a perfect connection, but it's very, very tied in. I couldn't quite hear.
To follow, knowing where the jet streams are?
Yeah, that does help us, yep.
Basically, it's a follow-up on the same question. Do you know at all, or do you have any knowledge about the interactions between the temperature of the water, the storm tracks, the jet stream, anything else, or as to where the atmospheric rivers are going to form so that you can make a predictive that this year is going to be like this year or a dud like last year?
Are you a scientist? That's a darn good question. All of the above. Yeah, we have studies going on basically in each of those topics, and folks here in the room, part of the group, are studying some of that. So the ocean temperature, we've got a preliminary analysis that shows maybe 10% difference in precipitation, just depending on what ocean temperature data we use, and getting that to be more accurate is very important. These aircraft data, we have someone working now, we're bringing that aircraft data into the model, and we're testing its impact. There's a lot of work going on in the various aspects of this, so yes.
It seems like an awful lot of water in these rivers. Where does that water come from? How does it get together into a river?
Another great question. So turns out a lot of it, most of it really comes from evaporation off the ocean surface. But these storms that form up tend to, the way the wind works, it can concentrate that water vapor into narrower areas. So it converges the water vapor, we say. And some of that is, most of it really comes from evaporation from the ocean surface originally. Some can come from evaporation from rain that falls into it, but that's a smaller percentage. So imagine a box. Imagine this room is a box within an atmospheric river, and the floor is the ocean surface, and there's winds blowing in from the sidewalls and then heading down that way. So the ocean's evaporating into our box. The winds are converging water vapor that's outside the room into the box. And then if the air's going up enough, it'll create clouds and precipitation, and that precipitation will rain that water out of the box. So it's a complicated balance, sort of a dance between those three processes, and then how they don't balance is when you get an atmospheric river amplifying, and when it rains out too fast, you have an atmospheric river decaying.
On the water management, totally different than this. You seem to be, is it correct that you said to us that a couple of decisions made by somebody not to store water made a big difference in how the drought worked its way in California? So the question is, who makes those decisions and how are they going to get better?
Well, there are a lot of very talented, dedicated engineers who work hard to make the right decisions in these reservoirs. And the rules to operate the reservoirs were usually created when the reservoir was built. Those rules basically said, if the water's on the ground, meaning in a rain gauge, in a stream gauge, or behind the dam, then that determines through a very special set of rules what the decision the reservoir operator needs to make is, release or retain. And that, remember, many of these reservoirs were built decades ago, or half a century ago even. And at the time, weather prediction was really in its infancy, especially when it comes to precipitation. So it was sensible to not have precipitation forecasts be part of the process, because big floods were happening at times, and anyhow, you don't want to get into that situation. But now what we're seeing is that the forecasts have gotten better, and this team I mentioned, that picture I showed of the 20-some-odd people, we've gotten together to try to invent a method to change that, such that we can prove out on a tabletop exercise, hypothetically, without changing any reservoir operations yet, that this could work or not. And we've got an incredible team, we've got good funding, and we're working hard on that. And right now, it's very encouraging. We're doing what's called a preliminary viability assessment. The official one will be released here in the next few months. And, from the inside track, I'd say, it's looking very promising.